Hi, I'm Daniel Dasse. I'm a PhD student at the Vrije Universiteit Amsterdam and the University of Amsterdam, and I'm working on knowledge graph construction from text. And today, in this video, I'll be talking about entity linking, which is an important step towards solving this problem. So, during the course, we have seen how different technologies enable the creation of large-scale knowledge graphs to represent information in a structured way. We can see in this figure this graph that shows the state of the linked Open Data Cloud as of July 2020, which helps us understand what can be achieved in real life. We can see interconnected resources ranging from general information, as in DBpedia, to more specific domains such as geographical data and even music. And what's even more interesting is that this vast amount of structured data plus other technologies also enable us to do things like answering queries, updating the graph, and visualizing subgraphs. But what about unstructured data? So there is a vast wealth of knowledge in a form that is not so structured, that is natural language. And we can take, for example, the combined research output produced across the world. For decades, the number of yearly publications has been increasing constantly, with more than 2 million articles published in 2018 only in the fields of science and engineering. News are also sources of information written in natural language that potentially convey factual information for which there is also a constant stream of data with thousands of articles published per day in different languages. And then we have user-generated content in social media with a growth that is staggering even when considering only 60 seconds on the internet, as shown in this infographic. So every second, 350 million tweets are posted in Twitter. Well, there is a lot of noise in a social network like this. We might also find interesting statements that could be interesting in the context of the knowledge graph of a particular domain. Like this tweet here by NASA, which is giving some details about the latest events on the Perseverance rover mission. So having seen this, we might be interested in enriching a knowledge graph or even creating one from scratch to take advantage of all the unstructured data that is available. Well, clearly the sheer size of this data means that it is not feasible to put humans in charge of reading it and putting it into structure form. We then need automated methods that enable computers to do most of the work for us. This has motivated multiple problems that have been addressed in natural language processing research. Some of these are first named entity recognition, where we must identify what words or spans in some piece of text correspond to entities, and also what's their type. So, for example, what spans of words are people, what are locations, and so on. We also have relation extraction, where we aim to find what is the relation between the entities that we detected in the text as intended by the document. And then lastly, in entity linking, we seek to find a mapping between the entities that are detected in the text and a canonical entity identifier in a knowledge base, such as a uniform resource identifier. So in contrast with these two previous tasks of named entity recognition and relation extraction, we can see that entity linking is itself tied to a knowledge base. And we can see that a successful system that implements these components can then take as input some text and output a structural representation that can be used to construct or enrich a knowledge graph, which is what we were initially aiming for. In this lecture, we will focus on the problem of entity linking. So we will start with a more detailed definition of the problem, then going through some solutions that have been proposed in the literature, some recent approaches to the state of the art, and then challenges that are still open in this field. So let's start by defining in a bit more detail the problem of entity linking. We assume that we have access to a knowledge base with a predefined set of entities E. And then, given a piece of text, the problem of entity linking consists of mapping each mention of an entity in the text to an entity in the set of entities E of our knowledge base that fits the intended referent in the context of the text. So let's just look at an example. We have here our knowledge base, which is Wikipedia, and then an example sentence that says Amsterdam is the capital of the Netherlands. And here in this case, we can see that the spans Amsterdam and the Netherlands have been detected as entities, so these are the mentions that we want to link. And which means that if our knowledge base is Wikipedia, an entity linker has to map these mentions to the respective Wikipedia pages for these two entities. Alternatively, if the knowledge base is not Wikipedia but Wikidata, we also know that Wikidata has entries for these two entities, so that means that the entity linker has to map the spans to the respective entries of Amsterdam and the Netherlands on Wikidata, which are shown here. So there are a number of aspects that make of entity linking a very challenging problem. The first set of challenges is related to the nature of the problem itself. So first, when given a piece of text, how entities are extracted from it determines the entity to which it is linked, or to which the entities are linked. And that means that we have to answer what is an entity, which sometimes is not entirely clear. We have an example here on the right. We have the sentence, the president of the US visited Vietnam. And then we have two overlapping ways of detecting a mention. In the first one, we would link the office of the president, whereas in the second we would be linking to the country, the United States. So the question is which one of the two is detected as an entity would end up in a different way of extracting entities from these sentences. And then another challenge here is that the intended referent might not be entirely obvious. So it is not exactly clear if, let's say, we stick to the way of detecting entities in the first case. So the president of the US is detected as an entity. It's not entirely clear if we should link this to the office of the president as a political role, or should this be the person that is currently occupying the position. These are questions whose answer is not entirely clear. Also, when defining the problem of entity linking, we noted that the linked entity is inferred from the context in the sentence or in the input document. But what if the context doesn't contain enough information to determine this? So Here we have a second example where we are given the mention Will Smith, which apparently refers to a football player, but unless we're given a much more specific context, it would be hard to link this mention to any of the multiple entities with the same name on Wikidata. So if you go to Wikidata and search for Will Smith, you will find, well, in addition to a couple of actors, both American and British, there is also these 3 football players. And as the sentence currently stands, it's not straightforward to determine which of these 3 the mention is referring to. And then we have the problem that entity linking can potentially be a search problem over a very large space. So as of today, Wikipedia contains more than 5 million entities, and in principle, any entity linking system over Wikipedia has to determine the correct entity out of all possible entities in this set. This means that solutions for entity linking also have to be scalable, and they have to be able to adapt to potentially dynamic knowledge bases. And then we have, well, much more problems that are even related to NLP tasks in general, such as the fact that language is ambiguous, there are changes of language use in society. There is also a lot of noise in data that is available online, among other problems. So now that we know that, well, entity linking is a challenging problem, well, people have still proposed different ways of trying to solve this problem, and we're going to take a look at this next. So here we have an example. This is basically our running example. And now what we can see in the literature is that many systems can be represented as a pipeline that first starts with the document, or in this case a very short sentence, and the text mentions in them. In this example, the word Amsterdam is detected as an entity. This can be seen as a special case of named entity recognition, which also selects groups of words from text, but where we don't necessarily need to predict the type of an entity. Usually, a named entity recognition or NER system would not only predict boundaries of words as entities, but also assign a type, like is this a person or a location or an organization. In this case, or in many cases in application of entity linking, we might not necessarily be interested in this information, only in boundaries of where an entity starts and where it ends. And that's the job of the mention detection step. In the next step, we then generate candidates. So these are entities from our knowledge base that are potentially entities that are referred to in the text. This process basically is narrowing down all the possible entities to link from around millions of entities that we saw that there are in Wikipedia down to a manageable set that ideally has high recall. One way to implement the candidate selection procedure is to rely purely on string matching. This can be implemented efficiently by building a search index built with names and also aliases of entities that exist in our knowledge base. And also the fact that an entity might appear with different aliases in text is important when solving this problem. So that's why we also have to take into account aliases when building these search indices. So assuming that our knowledge base is Wikipedia, this approach would result in a list that would probably look like the three cities that we have here in this figure. It's also interesting to note that two of these cities are not even in Europe, but nevertheless they are good candidates because they have a very good match with the word that is mentioned in the text, which is Amsterdam. We might also have other entities that are retrieved as this candidate selection procedure, such as a museum in Amsterdam. So as long as there is some overlap or some similarity, these could be potentially good candidates. And then in the last step, we have disambiguation, where we have to select from the list of candidates, we have to select the best match. The main idea at this stage is to use the context of the mention and its correspondence with the candidates to perform the final selection. So since at this point the number of candidates is much less than the number of entities, we can afford a more computationally expensive method that can match the context of the mention with the properties of the selected candidates. So before, when doing candidate selection, we were interested in reducing the number of potential entities from millions to probably a few hundred or even tens of entities. And now that we have such a reduced set, we can incorporate more elaborate algorithms. So one way to do this is to look at the textual description of the candidate, so of each of the candidates, if it's available in the knowledge base. We can see that this is the case, for instance, if our knowledge base is Wikipedia. We know that Wikipedia is basically a knowledge base of entities where every entity has its own page that describes the entity. And in this case, well, we have retrieved the description of the city of Amsterdam, and we can see that the context of the mention in the input sentence shares some words with the description of the city of Amsterdam in the Netherlands. So, namely, those words are capital and Netherlands. So this helps us see that there is a high overlap between the description of an entity and the context of the mention in the input sentence. So after a process of scoring all the possible candidates according to a heuristic like the one we previously described, we will be arriving at the final decision, which for our example would be the URL of the page in Wikipedia for the city of Amsterdam. So overall, this is how you can describe many of the systems for entity linking that have been proposed. There are different steps in this pipeline that are rather generic and can be applied to entity linking with knowledge bases of different types. Usually the traditional approach is, or a very common approach is that each of these steps is a separate tool, and they are all then chained together to produce an entity linker. But a potential downside of this is that any error that any of these steps introduces can then propagate towards other steps, and then it's just not possible to backtrack to a particular step to fix some error during linking. Now we can also see that disambiguation can be implemented in different ways depending on the type of information that the knowledge base provides. So now let's talk a bit more in detail about disambiguation. So we can basically say that there are two approaches towards disambiguation. At this stage, we already have a mention and a list of candidates, and now we want to select only one of the candidates. In the word-based disambiguation approach, we use descriptions of entities to disambiguate each mention independently. And what I mean by independently is that in this case, we only look at the mention of Amsterdam here within brackets as an entity in the sentence. We know that there are other entities in the sentence like Netherlands, but when doing disambiguation with this word-based approach, which is also local, we look at each mention independently from any other mention in the sentence. So, and then what we can do is to use the context of the entity in the text and try to match it with the description of the entity. And this is essentially the approach that we described earlier as an example. And this is an effective approach if we have a knowledge base where entities have descriptions like Wikipedia. Now, instead of considering each mention independently, we can first annotate all mentions and disambiguate them collectively. This is done in the graph-based approach, or this is also known as a collective approach. In this case, we can build a graph that contains nodes of two types. So we have nodes that correspond to mentions detected in the text, and then nodes that correspond to entities in our knowledge base. We then create edges between mentions and their candidates, and also between candidates for all mentions. So here we can see that linking the mention of Amsterdam to the city in the Netherlands is consistent with the mention of the Netherlands and its candidate. So note that this approach requires us to have access to a graph that relates entities in our knowledge base. As an example, we can use Wikidata or DBpedia, but even we can also build a graph from Wikipedia pages, because we also know that Wikipedia pages are interconnected via hyperlinks that we could potentially use to build a graph. So collective approaches are therefore better at enforcing that disambiguation is consistent by taking into account all mentions in a sentence. So in this case, we're doing disambiguation jointly for the mention of Amsterdam in this example sentence and also the Netherlands, in contrast with the previous approach that would only disambiguate first the entity of Amsterdam and then independently for the Netherlands. Now, when we look at how these systems for entity linking are evaluated, we see that the most popular way of evaluating these systems was defined in the Connell 2003 shared task on entity named entity recognition. So even though it was defined for NER, it was later extended to the evaluation of entity linking systems. And what we can see from this paper here is that they define precision as the percentage of named entities found by the learning system that are correct. Recall is the percentage of named entities in the corpus that are effectively found by the system. And we consider that a named entity is correct only if there is an exact match of the corresponding entity. So assuming that we have a text corpus where mentions are annotated with the correct entity in a knowledge base, we can determine when the system is correct because there is an exact match. And if the system links to an incorrect entity, this is counted both as a false positive and a false negative. Then with this we can compute precision recall, and F1 score. Okay, and now if we look at the state of the art, we see that most recent systems have started using neural networks that are jointly trained to detect mentions, disambiguate, and link with a single training objective. This is in contrast with pipelines that use different tools for different steps. And this would ideally solve the issue that we saw before, that we could have potentially different steps that would introduce different errors that would be difficult to fix later in the pipeline. These end-to-end methods go from text to linking in a single training objective, so now we have a way to correct errors that are introduced throughout the pipeline. Another trend that is recently apparent is the pre-training over Wikipedia. So we know that there are millions of Wikipedia pages that contain hyperlinks that can be treated as labels. So basically we have some text on Wikipedia and we can find mentions of entities, and it's basically the job of contributors to annotate some of these mentions with hyperlinks to other Wikipedia pages. And so this means that Wikipedia is basically a large training data set for entity linking. So this is a very common approach nowadays, to use Wikipedia to pre-train an entity linker. So we're basically taking advantage of the large scale of Wikipedia in terms of coverage of entities, and also the amount of text that it contains, to train an entity linker that can then be fine-tuned on a specific domain. So this means that once we have trained an entity linker over Wikipedia, we can then fine-tune over, for instance, probably small entity linking data set over a biomedical domain, for instance. And then lastly, as in many other NLP tasks, the state-of-the-art models that we're seeing nowadays for entity linking are based on using transformers, which are large text encoders. These are neural networks that are optimized to process text data. So in this table we can see the results for one of these most recently proposed entity linking methods, which is called Genera. So Genera is pre-trained also over Wikipedia, and then it is fine-tuned over AIDA, which is a standard data set for entity linking. Then usually these models are also evaluated over out-of-domain datasets, which are not used for any sort of optimization or fine-tuning. And the idea here is to assess the domain transfer capabilities of a system. So ideally we have this single column that corresponds to AIDA. This is an in-domain, which means that the models are fine-tuned or trained for entity linking over AIDA, and then they are evaluated over a group of out-of-domain data sets that correspond probably to other domains, or that have little overlap with the in-domain data set. So the metrics in this table correspond to F1 scores, and we can see that in most cases these models achieve a value higher than 90. But a common case where these models still struggle is, for instance, when coreference resolution is required before linking an entity to the knowledge base. So overall, we have seen a number of ways to do entity linking that are very effective, but overall there are still some open challenges towards solving entity linking. The most successful systems are based on supervised learning, which require a painstaking and expensive labeling procedure, sometimes even by domain experts, which can be quite costly. So while there have been some efforts towards using partially labeled data, this is still work in progress. Another issue is coreference resolution, which is particularly difficult since not all datasets for entity linking consider labeling coreference as well, and this is instead treated as a separate NLP task, which means that probably we have to use a separate component for coreference resolution, train on a different dataset, and then transfer to our entity linking problem. But then again, this introduces the problem that we've discussed before about using external tools that can introduce errors that then propagate into our entity linkers. Data-driven approaches like neural networks can also be biased towards highly frequent entities, so that if they perform well on them, the apparent performance will be good. But this does not necessarily mean that they also perform well over infrequent entities, and in fact, it has been shown that these models perform poorly with them. So lastly, there is still ongoing work on determining what to do when an entity is not in the knowledge base. Many of the systems that we saw, for instance, in the state-of-the-art, are only evaluated over entities that are in the knowledge base. But it might also happen that there is some entity that the system detects but is not simply in our knowledge base. And it's not clear what we should do in that case. Or should we link to an out of knowledge base symbol, or should we create a new entry in the knowledge base for it? And then this on itself is also an important question. So when should we create a new entry in the knowledge base, or how can we differentiate between an entity that exists in the graph and one that doesn't exist? So these are questions that are still under research and paint a challenging but exciting future for entity linking. And if you're interested in reading more about entity linking, I have also added a few references here. So these are reviews of entity linking that describe a little bit more about the story and the current trends. There's also a very interesting discussion methodology that asks whether the way we're currently evaluating entity linkers is the best, or what assumptions are actually valid or not. And then lastly, there is just a selection of some recent methods for entity linking. Thank you for your attention.